All right, so our next unit of study is about entropy and the second law of thermodynamics. Let's start by considering a reversible and quasi-static process, a cycle in the PV plane. So we'll start at A. So there's an isometric process, isothermal, another isometric, and then we're back again to point A. And we're going to find Q, the thermal energy transfer, the work done, and the change in internal energy for each step in that process. So there's a chart here. So first of all, from A to B is an isochore, or isometric. So there's no area, there's no change in volume. So consequently, the work done is nothing. So by the first law of thermodynamics, a change in internal energy will be equal to the thermal energy transfer. But for a constant volume process, that's just NCV delta T. So we can just say NCV delta T. I was going to write dt, but that's dq. After you integrate, it just becomes delta T. And so that is NCV. And the final temperature is T1, and the initial temperature is T2. So we're going down here, a decrease in pressure. So that is T1 minus T2, and delta U will just be the same. Now, because T1 is smaller, this is actually a loss of internal energy. So this is thermal energy transfer out, or negative. That will be overall negative because T1 is smaller. So there's a flow of thermal energy out of the gas and therefore a loss of internal energy. Let's consider the next process from B to C. Well, that's an isotherm, and because it's an isotherm, the change in internal energy will be zero because the internal energy depends only on T. I suppose I should write here isochore. I just don't have enough room there, and this is an isotherm. Okay, so the work is negative integral P dV. We use the ideal gas law. That's equals P is nRT over V. T is a constant, so that comes out of the integral. And then we're integrating dV over V from our initial point to our final point. That, of course, is ln V. So it's ln V from final to initial, but ln V final minus ln V initial is ln VF over ln VI. The final point is V1, and the initial point is V2 on our diagram. So that's minus nRT. Sorry about that. That's in here, so minus nRT natural log of V1 over V2. Now, V1 is actually smaller, so this is less than 1. So the log is actually a negative number, and you multiply by the negative, it's going to be positive. So this is going to be overall positive, and work is being done on the gas, compressing it from a bigger volume V2 down to a smaller volume V1. Now the thermal energy transfer, because this is an isotherm, is just going to be the opposite of the work done. So it's going to be overall negative, and it's just going to be nRT ln of V1 over V2. So we just drop that minus sign to take the opposite. And again, because V1 is smaller, this will be a negative number, and so there's thermal energy flow out of the gas. Okay, C to D is once again an isochore, so no work is done, and the thermal energy transfer is NCV delta T again, so T final minus T initial. And because work is zero, the change in internal energy is just the same as the heat transfer. And because there's heat flowing into the gas because T2 is greater, there's going to be a gain in internal energy in this process. It's NCV T2 minus T1. Okay, the last process from D to A is again isothermal, and so there's no change in internal energy because U depends only on T, and again it's minus integral P dV. We make exactly the same substitutions as above because it's constant temperature, and our T comes out, and we end up integrating dV over V, and the integral ends up being the same, V final over V initial. The only change here, of course, is that the from D to A, the final volume is V2, and the initial is V1. So our expression ends up as negative nRT ln of V2 over V1. Once again, the work is the opposite of that. Now, because V2 is actually bigger, this is a positive number, and so the work done in this case is overall negative. So work is actually done hold on a second there. Okay, so what I'm trying to say is work is done by the gas, and therefore the work done is negative. And the thermal energy transfer is going to be overall positive, meaning heat flows into the gas, and it's nRT ln V2 over V1. Okay, so for the overall process, if you add this and this, they cancel each other out, and it makes sense for a closed loop. You're ending up back at the same state. Use the state function. It should be the same. But when we add up these works, it's not 0. Because this temperature here, and I should have made this a little bit more clear earlier on, this isotherm is actually at temperature T1, and this isotherm is at temperature T2. So these two aren't opposites of each other, and consequently they do not cancel out. So adding this and this, what you get overall is NR, and then it's T1 minus T2 ln of V2 over V1. And you can do that just by taking the reciprocal of this, which introduces a minus in front of the ln. So it ends up as positive T1. That's how this term comes about. Okay, and by the first law of thermodynamics, we know that the thermal energy transfer has to be the opposite, or you can just add this one and this one. These two do cancel out, but these two don't. So you just end up with it the other way around, nR T2 minus T1 times the ln of V2 over V1. Now, because V2 is bigger, and T2 is bigger, so this ends up positive, but this ends up negative. So this is overall negative, so you get work out, work done by the gas, or work out. And this will be overall positive, so there's heat flow in. And here you're getting work out, or work done by the gas. So what we see is that U is a state function. You do a complete loop, you end up back in the same state, there's no change in internal energy. But neither work nor heat is. And I suppose that's useful because in this cycle, we've managed to convert some thermal energy into work done. So this would be an engine. But we would like to look for a state function related to thermal energy flow. So we just did this full cycle like this, and we ended up at exactly the same point. And there's no change in internal energy. Okay? For a state function, a full loop in the PV plane gives no change. All right, now, Q and W are not state functions, and we've said that before. They're not even really functions, right? Because there's no functional form for W unless it's reversible and quasi-static, in which case you can write dW as minus the PdV, and you can write dQ as nc delta T, or nc dt. We would like, though, a state function for Q. So for that reason, I could say here they're not state functions because in a loop, the sum of the Q's is not 0, and the sum of the W's is not 0. But there is a state function that's related to thermal energy transfer, and it ends up being defined as follows. The change in a function, and it's S that will be the state function, ds, is defined as not dq, but the ratio of dq to the temperature at which the thermal energy transfer is happening. Now, this is only true for a reversible process because dq isn't well defined otherwise. So let's just show that for this definition, that for our previous loop, our previous cyclic process in the PV plane, that we get 0. We'll go through that same loop. So we start with the isochord from A to B. And we're going to find the change in this function S. So that is adding up ds, and we're starting at A, and we're ending at B. And I'm going to change to a finer pen. Okay, so we just said that ds was dq over t from A to B. And this is an isochord process, so dq is n cv dt. And we've got to integrate that, divide that by t, and then integrate again from A to B. Okay, well, n and cv get pulled out because they're just constants. And then it's ln t from final to initial, but then we subtract, use the log property to get that ratio. Okay, now the temperature at point B, I should say, I probably should put that back here, was temperature T1. And then in state A, the temperature was T2. I probably should have had better limits there. Okay, next, from B to C, that was the isothermal process. So T is going to be a constant here. So delta S is the integral from point B to point C. ds, and ds is dq over t. T is a constant, so it comes out. Now, which t? Along this isotherm from B to C, the temperature was T1. So now we're just adding up dq between B and C. Well, adding up dq along B and C is just going to give you the total q that flowed in between B and C. And we calculated that previously just by computing the work that was done, because you can't find q directly along an isotherm. But on the previous page, it was argued that heat flow was minus nR T1 ln of V2 over V1. And you can see already what's going to happen here. These terms didn't cancel out either because the temperatures were different, but now those temperatures are going to cancel. So the changes in the state function S are going to end up canceling each other out because of that. Okay, so next, the isochoric process from C to D. We evaluate delta S. It's the sum of all the little DS's between C and D. So ds is dq over t. And because this is an isometric process, dq is n cv dt. And that, we pull out the n and cv, and then it's dt over t. Of course, is natural logarithm. And then we've got to do ln of temperature D over temperature in state C. That's n cv ln of, well, temperature D was T2, temperature C was T1. Just to see a little easier that it's going to cancel later, we'll use the log property, and a reciprocal is a minus 1 power, which I can pull out in front using the log property. So if I take the minus 1 back in, that's probably easiest to see. So a number out in front of a log can be brought in as an exponent. Bringing in the negative 1 power creates a reciprocal, and so it takes it back to this expression here. So we can see the same. Next, along the isotherm again, as we did above, we're going from D to A. T is constant, so it comes out. Then we end up adding up dq, which of course is the thermal energy transfer from D to A. We worked that out previously by finding the work, because you can't find dq directly for an isothermal process. So that's 1 over T nRT ln of V2 over V1. Now, these are along the temperature 2 isotherm, and again, that now cancels out. So this term is now the opposite of this one. So when we add it all up, we get no overall change. Now, that is consistent with S being a state function. A state function is one that depends only on your location in the PV plane, only on the state of the function, and not on the path you took to get there. Now, that's no proof. That's only one process. But it turns out that for any loop in the the PV plane, delta S is 0. So then we conclude that it actually is a state function, and it has a name. It's called entropy. And we're going to be dealing with entropy for the next 4 classes, and we're going to be led to the second law of thermodynamics, which fundamentally places limits on the useful amount of energy we can extract from a process. But that's our pre-lecture video.